Okay, hello everyone. Welcome back to today's lecture. I told on myself to the higher-ups that we finished all the content way too quickly on Monday, so we're adding a little bit more to the end of this lecture just in case, so probably not leaving 30 minutes early today. Sorry. So just double check that you have the right notes. I think I updated a new preview set of slides yesterday, so if you skip to the end, there should be some information on directing groups and activating, deactivating. So just check for that. TA office hours are tomorrow, 11:30 to 1, so that's Sarah and myself answering your questions for the midterms. Canvas Quiz 5, closing on Friday, midterm 2 next Tuesday. Design a question, I think the last day to do that is Friday. But good news is problem sets are now up as well as practice midterms. So problem set answer keys should be coming out tomorrow, but it's always good practice to try the questions before looking at the answers. So those are the updates. And so last class we covered 3 sort of similar reactions: nitration, sulfonation, and halogenation. And that included generating an active electrophile and then reacting it with a simple benzene ring. And so before we move on to today's content, a little review question for you all. It's a couple minutes. Probably won't need that much time, but yeah, a couple minutes to do this review question. All right, so does anyone want to tell me what these reaction conditions are for? Clemenson. What is a different reduction condition we could use if we have acid-sensitive groups? Yeah, the Wolff-Kishner. And then the product for this reaction should be 5-membered ring with the stereochemistry still intact, with the only thing deleted being the carbonyl. Great. All right, so today's lecture we're going to be covering 2 more reactions. So the similar generating a great electrophile and then reacting with the benzene ring. And then we're going to move on to the other content that was added, which is directing groups and figuring out if you already have one of these substituents on your benzene ring, what's going to happen next if you want to. Sorry? Yeah, sorry. You would want dehydrating conditions for that, right? If you're thinking about getting rid of this hydroxyl group, you need dehydrating conditions. So like just acid and heat, but right now we're in aqueous HCl, so yeah, there's no driving force to get rid of the water. Yeah, great question. All right, I'm going to move on. So 2 active electrophiles and then the directing groups. So the Friedel-Crafts, this guy had a great career and got his name on 2 reactions. One of them is adding an alkyl group, so that's like a hydrocarbon. And the other one is adding an acyl group, so this carbonyl. With some other sort of alkyl group substituent coming off of it. So this is important to note. The Friedel-Crafts alkylation is a way to make a carbon-carbon bond on like an aromatic ring. So whenever there's like a carbon-carbon bond formation, you want to keep that in your head because those are kind of hard to make. So in this reaction, you want to use a metal catalyst, so a fluid acid catalyst, and a haloalkene. So you also want to match the metal halogen, the Lewis acid, with the haloalkane. So if you're using aluminum trichloride, you would want to use that with a alkyl chloride. And if you use like aluminum bromide or iron bromide, you would want to use a halobromide. So just want to match those. Yeah, so the first thing we want to do is generate a really active electrophile. So how we're going to do that is use one of these lone pairs, attack the aluminum trichloride, which would generate this. And then we're going to move the double bond or the single bond from this chloronium atom and generate a carbocation and this aluminum species. And then this is our electrophile. Yep.
Why don't we have a double bond between the silver and aluminum? Because we already need one bond and then
Yeah, great question. I'll redraw this arrow. It should be going from the double bond onto the chlorine. All right, and so once we have that electrophile, or I'll leave it up for a couple more seconds. Once we have that, oh, here's the nice one. Then this should be really common if you were here on Monday. We're going to use a pi bond from the benzene ring to attack the carbocation. And then we're going to use the base in our reaction, which is this aluminum species. But it's actually going to be the chlorine. So we're going to take one of these bonds and use it as our base to extract the hydrogen. And that's going to go and re-aromatize. And then we should have HCl and our Lewis acid catalyst. So it's regenerated. And here it is, all nice up on the screen. Any questions so far? All right, so these are 2 try it later questions. They're really straightforward. There's no funky twists in them, so should be able to get these pretty straightforward. Yeah, good practice. For alkyl halides, something to consider is that it doesn't really work well with primary halides. And can anyone venture a guess as to why? Yeah, it is not good with a primary carbocation. So you would never really use this species with this reaction. Does anyone know why? Yeah? Yep, and so what would happen if you generated it? Yeah? Getting there. It would do something before it reacted with the benzene ring.
Is it like carbocation rearrangement? Because there's no like hyperconjugation.
Yeah, so it would do a hydride shift. So essentially what you're going to do is form this initial carbocation, but that's really unstable because it's primary, and so you would do a hydride shift to form the more stable secondary carbocation. Yep. If you have chloromethane. That's a great question. It would probably just methylate, yeah? Would you want to work with that in species? Probably not, but yeah, that's a great question. There's nowhere for it to go. Would work, should work. Yeah, so essentially you can't really form a primary halide and get good selectivity with this because you're going to be generating the primary, which may react with your benzene ring, but more than likely it's going to do a really fast hydride shift, and then you're going to react with the secondary carbocation, and you're going to end up with a mixture of products. So you might get some of what you want, but you'll probably get most of what you don't want. And then that would be a really sad day in the lab for you. You have to go back and do it again. So this would be minor, and this would be major. So a try it later question is to work through this, figure out whether or not it forms a primary or secondary or tertiary, and then predict the final product. Oh, actually, this is an example. Oops. So we'll do it together. This would be our initial electrophile. But then we have this hydrogen here, and so it would do a hydride shift. Forming our secondary carbocation, much happier. And then our final product would be this species. Yes?
In that a situation where it's like secondary versus tertiary, would it be the same kind of situation?
Yeah, it would probably go from the secondary to the tertiary, but it also depends on like other factors, like maybe what temperature you're running it at, because yeah, temperature really controls a lot of things, and like if you have enough energy, then it would probably shift. Yeah, it depends. Yep.
Sorry, is the hydride shift not towards the tertiary carbocation?
Sorry, what do you mean? Oh, this is a this is a tertiary. Is that the question? Great. All right. Now these are try it later, so explain why this one's the major product and this one's the minor product. Pretty straightforward. So for the Friedel-Crafts, again, it has to be an sp3 hybridized carbon, so it has to be a haloalkane. So you can't have it where it's a vinyl carbon or like a vinyl halogen or a aryl halogen. It's just not reactive enough. And the carbocation you generate really isn't that stable. So it has to just be, so this one wouldn't work, and this one wouldn't work. So it's really just the primary or the sp3 hybridized. again, and what we're going to cover later is if you install an alkyl group, you're actually increasing the reactivity of your aryl ring, and so getting monoalkylation is super difficult. You're likely going to increase the reactivity of your ring, and then that will react with more of these species in the solution rather than having another undecorated benzyl group reacting. So another thing to consider is if you have other substituents on your ring that are incompatible with these reactions. So the nitro group is one of them, probably just because it's super deactivating, which again we'll cover later. But yeah, there's a couple substituents that aren't going to work. And lastly, what we covered is primary carbocations are really unstable and they want to rearrange. So you're going to get a mixture of products, most of what you don't want. So you might be thinking, there has to be a better way. And it's true. This is what this guy did, is he came up with another one. Why don't we put an acyl group on and then use, say, the Clemenson reduction to get rid of the acyl group or the carbonyl and to end up with the alkyl group that we really wanted in the first place. So this is another important reaction to know, Friedel-Crafts acylation, and it's generating this acyl group on it, which can then undergo reduction to form an alkyl group. So to go over the mechanism, once again, we're forming a highly activated electrophile, and then we're going to react it with an undecorated ring. So we're going to take this lone pair, attack the aluminum trichloride, and form this unhappy, positively charged halogen species, which will then go fully onto the Lewis acid, and we're going to form this resonance stabilized acylium ion. And that looks really nasty until you remember that we can kick down that lone pair and form like an oxonium looking species. And then that is our active electrophile. All right. And then this is the mechanism drawn nicely. Yep. Mm-hmm. Oh, it's this species. It's in resonance. So both of them are present, and this is the active position, but this whole species, because it's the same species, is the active electrophile. You're going to draw it with the positively charged carbon, because the oxygen can't react and like form a bond there. It's just the carbon that gets formed. So I'll redraw this arrow to point to this whole thing as the active electrophile. Is that helpful? Any more questions? Okay. So again, this is the nice one, and the acylium ion, so this species, which is in resonance, is not susceptible to rearrangements because it's in resonance. So because this lone pair can come down and stabilize this carbocation, you're not going to get a shift with, say, something down the line here. So like if we had this, you're not going to get a hydride shift just because the oxygen lone pair can come down and stabilize it. So you're not going to get that. Mhm.
What if you had an alien group on the side, and then now if you have that shift, like the positive charge on the nitrogen is more stable than the oxygen? Would that
If you had like a nitrogen like this,
yeah, like there's also another alien on that carbon, so it's that halide shift.
oh, so like go down here and then go like that? Possibly. I don't know the answer to that. I'm trying to think of a chemical that would have this configuration. It all depends on reaction conditions. You probably would have a small amount of this, but yeah, maybe you would want to design your molecule and your synthetic route in a way that you would avoid this. But maybe. I don't know. Okay, so for the mechanism, again, we've seen this before, and this is now the 5th time we've seen this reaction mechanism, so it should be really easy. Double bond comes out, reacts with the carbon with the positive charge on it to generate this intermediate. With the positive charge, and this is resonance stabilized again. And then we have our Lewis acid base now come in. And we have one of these carbon or chlorine lone pairs come in, act as the base to regain aromaticity. And once again, we've regenerated our catalyst in situ, along with HCl. Mm-hmm. Mm-hmm.
You know, like when you generate like the carbon and the oxygen, right? I was just curious, would the positive charge rather be on the oxygen or on the carbon?
So the question is, between the resonance forms, which one would it rather be? Would it rather be on the oxygen? Like which one's the more reactive? Which is a question we had earlier. And remember that a resonance form, it exists like as both. And so it's not necessarily going to be one or the other, but you're typically going to have like a charge density sort of spread out over the molecule. And so this is the reactive position is on the carbon, because the oxygen can't form another bond. So you're going to have to come in and with like a nucleophile and react at this position to get rid of the oxygen. So remember, it's just like this carbon is what is electrophilic rather than the oxygen. Yeah. All right. So this is a throwback to the original deep cut review question. You want to reduce this carbonyl with a Clemenson or a Wolff-Kishner, depending on what else is around in your molecule. Typically, a Clemenson works better just because it works better on benzylic carbonyls. But again, if you can't use the Clemenson, if you don't want to, say, reduce a ketal or like remove a ketal, then you would have to use the Wolff-Kishner. So pretty redundant. So it depends really whether or not you want to use the alkylation or the acylation. It's up to you whether or not you need to generate a primary carbocation or a primary alkyl chain, or if you think your alkyl group is stable enough not to undergo hydride shift. It depends. In the lab, you probably would want to be safe, do acylation then reduction, but again, it really depends. And if you're worried about polyalkylation, so if you have one alkyl group and you don't want to add more around your ring, then you would want to go to polyacylation. So that's the one with the carbonyl. Just because it's not going to undergo further acylation, and we're going to cover that later as to why. So this is a fun example. I'll give you guys a minute to try it, and then we'll go over it. Maybe 2 minutes. Yep, we'll go over it on the screen soon. All right, so the first step for this is we need to generate our electrophile. So we're gonna do the following, which is add it to the aluminum trichloride, and then we're going to do the elimination to form this species, an intermediate species. Which is in resonance with the other form. And then, does anyone want to predict where it's going to react? It would be a 5-membered ring, and I think I drew the double bonds in the ring in a confusing way, or a not very intuitive way, but we would want to have it there. And then we would go and react with this lone pair, or this pi bond. And then our resulting species after re-aromatization would be this 5-membered ring with an acyl group in it. And then this intramolecular reaction is way faster than if there was another one of these in the species, in the solution. So it would do an intramolecular over an intermolecular. So typically intramolecular is always faster, like 10s to 100 times faster. Something to keep in mind. All right, this is a try it later question for you. Explain why this product can't be made with either the alkylation or the acylation, and explain why. But that's for later, as well as this for later. This is for later, so propose a synthetic route to take this undecorated ring and add a alkyl chain. So to recap all of the reactions we've covered in the electrophilic aromatic substitution unit so far, we've covered nitration, sulfonation, halogenation, and then the 2 Friedel-Crafts reactions, the alkylation and the acylation. Once again, it all starts with forming the superactivated electrophile in situ and then reacting it with your aromatic ring. Not very nice conditions. Once again, you're adding 2 nasty acids together. This one, you're making fuming H2SO4. Not very nice. This one, you're using bromine, which if you've ever used it in the lab, it's like a red liquid that will corrode basically everything, and it will give off fumes as well. And then these ones, these aluminum species, are not the most fun to play with either. So these are harsh reaction conditions, and you're forming like super reactive electrophiles, and you also want to consider what else on your molecule might react. And so now we're going to move on to the next part, which is if you already have a substituent on your aryl ring, so we're going to call it G, and you want to add a second one. So let's just say you have an alkyl group or a carbonyl adjacent. What's going to happen next? Where's it going to react next on the ring? Is it going to be a fast reaction or a slow reaction? So we're going to go through some of the theory behind that and yeah, by the end of this lecture, hopefully you'll be able to predict pretty well where the groups are going to go, and it will follow. If you understand the concepts, you'll be able to figure this out on the test, and you don't have to memorize exactly what it is. You should be able to logic it through, rather than memorize what each position does. So a substituent can either be activating or deactivating. So essentially, it can either increase the reactivity of your benzene ring or decrease the activity for any other additions. It's just, is it going to react faster or is it going to react slower? That's pretty much it. Then a second thing to consider is where on the molecule is it going to react. It can either be orthopara directing, so these positions, that's orthopara, and then these positions are meta to the G substituent. So these ones are ortho. Oh, that's not how you spell that. And then this is meta. And this one is para. So that's the second thing to cover. What's also important to note is that if you're doing a reaction and you have something like a monosubstituted and you're going to try and add another thing to the ring, all of these positions are going to react. So it's less of it will only react at one position, and you're going to actually be forming sort of a distribution of all the products. You might have some ortho, some para, some meta, but depending on the activation and the directing group, you're going to get greater yields of one of these over the other. That's, it's important to know you're going to create all of them. And also, knowing that you're going to create all of them, it's important to not heavily rely on that, especially if you're doing a synthesis on a test. Don't be like, oh, it makes them all, and so I'm going to take like something that I know is typically orthopara, and I'm going to use it as a meta director in my synthesis just because I want it in the meta position. I wouldn't do that because you might be making like 5% of the meta product, and that would be a not fun day in the lab to try and isolate your 5% from your 95% of everything else. So ortho substitution, if we have this initial ring and we use this pair of lone of electrons to react with an electrophile, we're going to be creating this intermediate whereby a positive charge under resonance will either sit at this position, or this position. And again, if we're sort of averaging out all the resonance structures, we're going to get a partial positive charge on each of these positions. And so does anyone want to tell me if G, so this substituent is electron donating, is the complex stabilized or destabilized? Stabilized. Yeah, the complex is stabilized because if you have a donating group and it wants to give its electrons to the ring, it's going to be stabilized. If it's electron withdrawing, then it's going to be destabilized. That's also important to remember. For meta substitution, if we then add a electrophile at the meta position, we're going to form these resonance forms with the positive charge on each of these. So if G is electron donating, is the complex stabilized or destabilized? It will be through induction stabilized and through induction destabilized, but it's not as nice as if you had like a donating group right where the positive charge is forming. So it's going to be a lot less, and this is going to mainly fall into whether or not the ring is activated or deactivated. So the effects are much less. So again, mainly induction is happening for these. So this is what you're going to do on your own. Try para substitution. Should be pretty similar to ortho substitution. Go through, if it's a donating group, is it stabilized, destabilized? Same with withdrawing group. So activating and deactivating groups, these ones are pretty, I think this concept is really solid to understand, so hopefully won't be too big of a problem. When you are considering resonance and induction, if you are adding electrons to your ring system and treating it as a nucleophile, you're obviously going to be activating your ring because your benzene ring is trying to act as a nucleophile. So if you add electron density, it's going to be a better nucleophile. And if you remove electron density through an electron withdrawing group, your benzene ring is already like, well, I don't really want to react. I don't have enough electrons to do this. And then if you have an electronegative group that's also pulling away electron density, it's going to not be stabilized at certain positions. So your resonance and inductive effects can reinforce each other. So they can both like promote reactivity at certain positions, or they can both demote reactivity of your overall ring and at certain positions. So when they're in opposition to each other, you really have to consider which one is a stronger effect, and that stronger effect will win over it. So typically, for all of those options, you can have something that's strongly activating, you can have something that's mildly activating, mildly deactivating, or strongly deactivating, and we'll see examples of that later. So the first example we're going to go through is aniline. And so aniline has this nitrogen group, which is in itself electron withdrawing. So induction, this is slightly bad. But for resonance, this is a great addition to this ring if we want to activate it. Because we can make this resonance form. And we can make another one. And then a repeat of the first one, but on the opposite side. And so for resonance, this is amazing. So overall, this is an activating group for the ring. It is making it a wonderful nucleophile. And this one is an ortho-para director, just because you're putting this partial negative charge on the ortho and para positions. All right, we're good with this one. You want a couple extra seconds? All right, the next example we're going to go over is a nitro group. So a nitro group is extremely electron withdrawing. So it's going to want to really suck out electron density for the ring. So this is overall bad, really bad actually. And if we draw the resonance forms, we actually see we get a slight positive charge on all the ortho-para positions. And so resonance-wise, this is really, really bad. So it's awful. And so overall, this group is pretty strongly deactivating. And because we really don't want to react out of the ortho-para positions, it's going to be by default a meta director. Because if all the options are bad, meta is the least bad. And just to demonstrate how bad this is, this nitrobenzene is 100,000 times less reactive than benzene. So if you're wanting to add another group, or if you want nitro and a second group, you might want to consider putting the other group on first. unless you need it meta. So this is for you to try later, is a methyl group or an alkyl group. This, yeah, methyl or alkyl, they'll both exert the same. This is toluene. This is in paint thinner. Another one to try later is if we add an acyl group, so that's a callback to the Friedel-Crafts acylation. How does this affect the ring and its reactivity? And again, as a hint, remember polyacylation is not very favorable, so that should give you a hint as to whether or not it's activating or deactivating. The one we'll talk about here is halogens. Halogens are an exception to the rule because in chemistry you really can't have a rule without having many exceptions to it. So these ones are deactivators because they are electronegative, so they're slowly pulling out electron density from the ring, but if you draw a resonance form for it, you can actually put a negative charge on the ortho-para positions. So if we draw the resonance form, we can draw this protonated chlorine species and another resonance form. And then the last one is flipped. So overall for induction, this is bad, but for resonance, it's good. So it's slightly deactivating, but it is an ortho-para director. So this is a good exception to remember. Any questions? All right, so this is a review and sort of a lovely table and scale. So way off in the back corner, we have really strongly deactivating groups. These are groups that you really don't want to put on first if you have to do another addition to your ring. So they're strongly deactivating, and these are meta-directing, just because meta is the least bad option to react at. But again, all of these are going to create all the additions at all the positions, but you're going to have a greatest proportion for these strongly deactivating ones at the meta position. For the mild deactivating ones, this is, I guess, the answer to the try it later questions. But this acyl group is going to be mildly deactivating and a meta director, and that will be because it is electron withdrawing, and you can't really put a negative charge on the positions. You're going to, if you draw the resonance forms, you're going to be placing a positive charge at these positions, at the ortho-para positions. And then the halogens are the exception. So these ones are mildly deactivating, but they're ortho-para directing. Benzene is our reference. And then if we go to the activating side, we're going to have our benzyl alkanes, and we're going to have our ethers, and really strongly activating, really reactive ones, we're going to have aniline and phenoxylate. So we can see that if we throw the negative charge into the ring, we're really making a super active nucleophile for our aromatic reactions. So 2 examples to go over. If we have a fluorine ring or fluorine on our ring, this one's a halogen. So for a halogen, it is mildly deactivating, but fluorine is pretty electron negative, so that will be more deactivating than if we had a chlorine or a bromine. And it is a meta director. Nope, it is an ortho-para director. Oops. So our product is going to be, we're going to get a mixture of this, and we're going to get a reaction at the para position as well. And then for the second one, this one is activating and ortho-para directing as well. And this one is a Friedel-Crafts alkylation. And so we're going to get 2 products, reactivity at the ortho and para positions. We're probably going to get mainly para products for both of these just because sterics do play a role. So likely you're going to have a little bit more of the para for both of these. But again, you're going to get a mixture of all of these. So these are all going to be the major. And you will get meta, but in small amounts. Oh, that's a really awful color. Woo. Okay. All right, and these are for you to try later, and that's it. All right. Thanks for coming, and practice midterms, and problem sets are up. They're up. Yeah. All right, welcome back to after lecture. I'm going to quickly go through the practice try it later questions. This first question is really straightforward. It's asking to predict the products. There's not any funky business here. Essentially, we're going to generate our electrophile species, which will be this secondary carbocation, and then that's going to react with the benzyl ring to produce this final product upon re-aromatization. And then this one, the active electrophile, is going to be a tertiary carbocation, so that's pretty stable. And the final product, again, after reaction with the benzene ring and re-aromatization, is this product. And you should be pretty familiar with this mechanism and the generation of these electrophiles because we went over it a couple times in class. For this practice question, this question is really getting at generating a primary carbocation and why that's unstable, and getting you to rationalize why this is the major product and that's the minor product. So initially, upon reaction with the aluminum trichloride, we're going to generate this primary carbocation, which will then undergo a hydride shift to form the more stable species, which is this secondary carbocation, which will then react with the benzene ring to form the major product. And depending on concentrations and other reaction conditions, you may get some minor product or no minor product, just because the shift is so much faster than the reaction. For this next question, is asking to rationalize why this product can't be made with the Friedel-Crafts alkylation or acylation. And it can't undergo alkylation because, let's go here, can't undergo alkylation because the species that is needed would be a secondary carbocation, and that would undergo a methyl shift to form the tertiary carbocation. So that would essentially, if we have a CH3 group here, that would do a methyl shift to form a tertiary carbocation. So in a similar rationale to why you can't have a generate a primary carbocation because it would undergo a hydride shift to form a secondary. This is essentially the same thing where if it can form a tertiary carbocation, it will by any means. So this would in situ be the reactive electrophile. And this, of course, won't give the product we want. And the second one we can't do is the acylation. So if this is alkylation, this is acylation, We can't undergo that just because we need a carbonyl and chlorine, so we need an acyl chloride, but we can't form a Texas carbon. The reagent that we would want, if this could exist, would be this, but this should scream out, eek, absolutely never, because it's a Texas carbon. So we can't form that to form our acylation species, and so we can't generate this with our Friedel-Crafts acylation. So this one does not exist. All right. To form this final product, this would be a alkylated species. If we wanted to form it with the Friedel-Crafts alkylation, we would need to generate a primary carbocation. So this question is asking for a two-step process. So first we do a Friedel-Crafts acylation. Friedel-Crafts, nope. That's the acylation. And our initial electrophile would be this acyl chloride. And then in situ, we would generate this species. And that would be our reactive electrophile. So after step 1, we would generate this upon rearomatization. And then we would do our Clemenson reduction. So that's step 1. And then we would do Clemenson. And the Clemenson conditions are zinc and aqueous HCl. And then we would essentially get rid of the carbonyl. And after the second step, we would form the product that we want, which is this alkylated product. All right, so moving on to directing groups and activation, deactivation of our substrate. We looked at ortho and meta in class, and the para essentially follows the ortho rationale, where if we add a Y substituent on the para position, that would generate a intermediate that would place a positive charge on these 3 positions. And so if we had a electron donating group, the complex would be stabilized, especially through resonance, if you can imagine having a lone pair being able to donate in. And then if it's an electron withdrawing group, we're pulling electron density out of the system, and that would destabilize these positive charges even more. And so with the electron withdrawing group, this would be destabilized. The next practice, try it later, is looking at how a alkylated benzene ring induces reactivity for further substitutions. So from this, because this is inducing, this is good for induction. Resonance, we're not able to form a resonance structure that would further stabilize the molecule, so it's none. So overall, this is a semi-activating group just because of induction. So it would be activating, and it is a ortho para-directing group. For that, we can't add resonance forms. No resonance forms. All right, second to last, try it later. How does an acyl group compare? And so this is directly relevant to the Friedel-Crafts acylation and why, if you want only mono substitution on your ring rather than a poly acylation or alkylation, you would want to use Friedel-Crafts, because you would only get mono alkylation or acylation, or mono acylation. And that's because this group is electron withdrawing, and so induction is bad. And if we were to draw a resonance form for this, we could imagine this lone pair going in and then it going up on the oxygen. And we would form this species. where we would actually place a positive charge here and a negative charge on the oxygen. And so if we followed that around the ring, we would see that overall we are forming our ring with partial charges of delta positive at each of these positions. So just likewise with the other meta-directors, this is going to be a meta-director just because of all the positions, meta is the least bad. So they're all bad, but meta is the least bad. So overall, it is deactivating, and it is a meta-director. And the last practice example is to predict the products. So we went over 2 of these in class, but essentially we want to look at this. So this is deactivating, and it is a meta-director. And so if we're adding chlorine to this system, or we want to chlorinate this ring, our final product or products would be orthopara. So we would keep that on there, and we would have chlorine here, and it's meta-director. So we would primarily get one product. Sorry, everyone. Primarily, we would get one product, which is just the meta-directed substituent. So just a chlorine here. And for this last example, we have Friedel-Crafts acylation. The ring, because it is an alkyl ring, this is activating, and it is an orthopara director. So overall, our final products this time are when it is at the ortho position and when it's at the para position. And just like we talked about in class, sterics could have an effect here, so likely you would get maybe a little bit more of the para product compared to the ortho product. And that is everything we covered in lecture 29. Hope that helps.